Count good triplets in an array. You are given two zero-indexed arrays, nums1 and nums2 of length n, both of which are permutations of 0, 1 till n minus 1. So basically, our nums1 and nums2 will have same length and same number of elements as well. And the elements also will be same inside these arrays. The only difference is their arrangement. The elements arrangement in nums1 and nums2 will be different. Okay. A good triplet is a set of three distinct values which are present in increasing order by position both in nums1 and nums2. So what does that mean? So a good triplet will be three values that are distinct and will be present in nums1 as well as nums2, but the condition is their position, the order in which they occur, should be in an increasing. So let's take this as an example. So for example, in this 2, 0, 1, okay, 2 comes before 0, right, and 0 comes before 1. Their order of the position is increasing, 0, 1, 2, okay. But in nums2 array, let's consider this is nums2, this is not the case, right? 2 occurs in position 2 and 0 occurs in position 0, okay. It's actually decreasing, 2, 0, it's decreasing, right? So this is not actually in increasing order. What will be a proper, you can say, the triplet will be the 0, 1, 3. Why? Because 0 occurs at position 1, 1 occurs at 2, and 3 occurs at 3, and it's an increasing order, right? And similarly, here 0 occurs at 0, 1 occurs 1, and 3 occurs at 3. So this 0, 1, 3 is also increasing. Just forget about this too, okay? So the thing is, it doesn't matter which location they are present in, as long as if the triplet is in an increasing position, okay, in an increase, if they occur in an increasing order fashion, then and it should also occur in an increasing order position, okay, the index, not the elements itself. Elements itself doesn't matter, it can be like increasing or decreasing, but their order in which they occur in the element should be, in the array should be in an increasing order. Hope that makes sense. So all we have to do is return the number of good triplets. So in this case, we will only have one good triplet because 2, 0, 1, but here 2 comes like after 0 and 1, right? So it can't be then, I think we have 1, 2, 3, but 2, 1, 3 in this case. So it's not going to be, it's only 0, 1, 3 and 0, 1, 3. Fine. Let's understand how we are going to approach this problem more clearly. Let's take the same array that we had. Now, how are we going to think about it, first of all? So, one way to think about it is we can store either of these array and map their indices. Okay, maybe we can take this, okay, this is nums2 by the way, nums2, and we can map each of the elements in the nums2 with its index. Okay, if we do that, then we can figure out the index of these elements in over one time, right? But how is that going to help us? So for example, if we are iterating through this nums_i, okay, nums1 array, okay, nums1, so with I index, okay, suppose our I is here at index 0 and our j is at index 0 here, index 1 here, and our k is at index 2 here. Then we can iterate k from 2 to 3, and once we find a triplet, we check if, I'll just come to that, what we are going to check. But once that processing is over, we can increment our j here, and then k will be j plus 1. So it will begin here and till the end of the array, right? We can have like 3 for loops. But what are we going to do in those 3 for loops? So as I mentioned, we will have a mapping, right? So what we can do with that mapping is pretty straightforward. We will gather our we will get our ith index. Okay, this index value is 2, right? So we'll get where is this 2 present in our nums2 array. It is present at this location, right? Okay, fair enough. We will store this value. Okay, then our j points to this element, right? So we'll check where does that occur. Well, it occurs here, right? So we'll store this index value at jth index in nums2, and then let's have k as well. Okay, so this will point to k, right? So this value's index in nums2 is 1, right? And now that we have all these, so we know that this is I, j and k will occur in an increasing order because we are going to run it from left to right, right? We are going to iterate it from left to right, nums1. But the thing is, in nums2, what we can do is, we can compare all the indices that we had stored. Like 2's index is 2, 0's index is 0, and 1's index is 1, right, in nums2. So then we can compare, is that occurring in increasing order? So first we had encountered 2, which is I, 0, right? 2 here is 0, but here it is 2, right? And 0 here is 1, but here it is 0. So 2 is actually greater than 0, right? So that's so what does that mean? It doesn't occur in an increasing order, right? So we can do that, and the time complexity will be O of n cube in that case. Here's the brute force way. So you can just look at the solution here. It's the same thing that I had explained just now, that we have this ith index, we store ith index from nums2, then we store jth index from nums2, mapping all of these, and then finally we just count. Okay, if and only if our count if and only if our condition is satisfied of increasing order, like if these I, j and k in the nums2 occurs in increasing order, only then we increment the count, and once we have that, we just return count. Okay, there are a couple of observations that we can make. But first of all, can we improve? Can we simply try to get rid of one of the for loops? If we can do that, then our time complexity will go from n cube to n square, and that will greatly improve it, right? So how do we do that? Consider this example. So as I already mentioned, that we are going to map each of these nums2 elements with their index. Okay, so let's say we have done that. Okay, now consider this element 1. Okay, if I have this 1 and I figure out, okay, I can figure it out, that the index in nums2 is 1 here. Okay, so 1 occurs at this location in nums2 and 1 occurs in this location in nums1, right? So what I can do is, I can check if there is any overlap or there is any common element between the left part of both of these nums array. So one's left has 4 and 0, and here in nums2 one has only 4. So the common part is 4, right? And similarly, if you can figure out is anything like overlapping in the right side of 1. Okay, so here it's 3 and 2, and here 1's right side consists of 0, 2 and 3, right? So the common is 3 and 2, 2 and 3, right? So what I can do now from this, what I understood, that if I include 1, then I can make 2 triplets. 4, I can consider 1 including 1, and then I can use 3. Or I can do 4, 1 and 2, right? Similarly, it actually, these occurs in increasing order because we are going to iterate in left to right order, right? And similarly, it occurs in the same increasing order because we are going to check the left and right if there is an overlap. If there is overlap between left, then definitely it occurs before 1, right? There is overlap between right, definitely it occurs before after 1, right? So in that case, what I conclude is my answer will be 1, the overlap that is on the left side multiplied by the overlap on the right side. There are two numbers overlapping here, right? So that means I can combine 4, 1, 4, 1 and two numbers here, right? I can make 2 triplets basically. So what I want to do is find left common and right common elements, and once I figure that out, I can count the triplets. So it will be nothing but left common multiplied by right common. Okay, and I can do this for all of these elements. So I just have to iterate this nums1 element, nums1 array once. Okay, and for each of these, I have to figure out the overlapping, right? I have to figure out whether this part, this entire part overlaps with this entire part, or this entire and this entire part overlaps with this entire part. So there are a couple of ways to do that, but if we are thinking of n square solution, then we can do it linearly, right? So we can have, first of all, for nums1, okay, one of the for loop, and inside that we can nest another for loop which runs from like 0 to the index. This index value we can actually find out through our mapping, right? So we can run from here to here, and we can check whether it's present, okay? All the previous elements that we have encountered is present, okay? But the problem is we can actually do it for this as well, but is there a better way? Okay, is there, like, we can avoid using another for loop? Can we do that? Okay, so the answer is yes, we can do it. Now I'll tell you how we can do it, and this is gonna help you for the most optimal solution as well. Okay, so just pay attention how we are going to do that. So I told you that we are going to find the common elements. So the easiest way to find the common element is just to have a set, okay, and we can just store each of these as we iterate through our nums1 array. We can store these elements, right? We have already seen. Now if we find this, okay, we find the index of nums2, okay, then what we have to do is we have to simply iterate from 0 to that index, and we have to check whether all the elements that are present here are also present in the previous set. If it is present in the previous set as well, then we can conclude, yeah, it's a common element, right? But now, so what can we determine from this? We can determine an uncommon, okay? So how many uncommon parts are there? So if there are like 2 elements here and there is only 1, right? So number of uncommon values in this section is only 1, right? 1 is because the length of this is 2, right? This is the length of 2, and common is 1, right? So the uncommon will be 1 as well, right? Now what I want you to understand, okay, first of all, let's print it out. So what I want you to understand is, once I have figured out the uncommon elements, okay, the uncommon number of elements on the left side, I want you to understand that we can use these uncommon elements to figure out the common elements on the right side. Okay, right array, right subpart of the array. How are we going to do that? It's actually pretty simple. So on the right side, okay, first of all, let's trim it out. Okay, trim our array, okay, on the right side. So this is the part that we have to check for overlapping with this part, right? Now the thing is, we have found one element as uncommon and one element as common. So this uncommon part can never occur in this, because we have already checked it. If it had occurred here, then we would have already added in our common. But because it doesn't occur here, it will definitely occur in this part, right? In this part. So we have one uncommon element in this part. That's what I want to tell you. Okay. So this entire range will have exactly one uncommon part. Okay, one uncommon element. And so what I want you to understand is this formula. So my right common elements will be len nums1 minus current. So what is len nums1 is nothing but, like, I'm taking, actually this has to be nums2, but the length is same. So the length of this, okay, nums2 array will be trimmed, okay, with the current minus 1. So current is 1, so 2, right? 2 elements. So I'm trimming it here, and this part has to be checked with this part, right? This entire part has to be checked with this entire part, and from this entire part I have to get rid of the uncommon number of uncommon elements, and whatever remains will be the number of common elements. You have to understand this. This is very important. So let me just repeat one more time. What I'm doing here is I'm first of all finding out common elements, okay, common number of common elements from the left side of both of these. Okay, once I know what is the common number of common elements between them, I also know the number of uncommon elements, because once I have this and the value I can subtract the number of common elements, and then I will get the number of uncommon elements as well, right? Now the trick is, number of uncommon elements can never occur on the left side, so definitely they are occurring on the right side. And if they are occurring on the right side of the nums2, that means that they are uncommon even here in this part, right side, because we have already found it in the nums1 previous set. Okay, so we are having this uncommon even on the right side. Understood? So that's why this formula comes up. So our O of n square solution will be something like this. So we'll have the same things, count as well as that nums2 index map in our brute force solution. The only thing is, we'll add this previous set. Okay, we'll populate our nums to index map, okay, mapping the values with its index, and then we are going to iterate through nums1, okay, and then we are going to check if it occurs. Okay, this check is actually not needed, but I've added it. If it occurs in the nums2 index, I'm going to find this current. Current actually is the index of num2, okay, index of num2 with of which element? This element, nums1 at I, okay, this element, but this element's index in nums2 array, okay, and my previous will be 0, so basically I am just keeping count of the previous elements. Okay, so what I'm doing is, I am first what I will do is, once I figure out this current, I will iterate from 0 to the current, okay, from 0 to current, and I'm going to check if my nums to j is in the previous set. So I'm just checking like in my previous set, which will basically store all the nums I, okay, all these index nums 1 values, whatever we have previously encountered, okay, that it will store. But what here I will do is in nums to j, okay, I'm going to iterate from j to current, okay, current we get it from here, right? So I'm going to iterate nums to j in previous set, whether it is present or not. If it is present, then yeah, I have found a common element. Okay, now once I found the common element, I need to find the uncommon so that I can get the right common elements, right? So I find the uncommon by I minus previous, right? And once I have the after, okay, once I have the uncommon, I can calculate my after. So how do I calculate my after? So it's a simple thing. I will first of all trim my array, the number of elements in the right hand side. Okay. And then I'm just going to get rid of the uncommon elements because it will be uncommon even in the right hand side. Okay. And here's a little check, like I don't want to end up in like negative values. So if I do go beyond 0, then I can just put a 0 here, okay, in this condition. And then finally, I will have my count. Okay, so once I'll update my count by multiplying previous into after. Okay, and of course, I have to update my previous set because whatever element I have encountered should go in my previous set. And then finally, I return my count. So this is my n square solution. So can we do even better? That's the question. So our solution is of O of n square. Okay. But can you understand where the bottleneck is coming from? Okay. What is causing the bottleneck? So we are actually, first of all, iterating from 0 to the length of nums1, right? So if we iterate from 0 to length of nums1, we can't actually get rid of that. We need a linear solution at least, right? But can we reduce the time that we take for searching the common elements? Because we are doing linear search to find the common element, don't we? Can we reduce it from linear search to uh, like a binary search or something like that? If we can do that, then I think we will have O of log of n time complexity, right? Only for that part. And then when we combine it, then we'll have O of n of log of n, right? So how can we achieve that? So the answer for that is segment trees. Now what are segment trees? Let's find out. So let me go in brief what segment trees do and how can we search in log of n time, or actually calculate the common elements between left and right in log of n time. So let's consider this array as our segment tree. So I'm going to depict a figure as a tree, but keep in mind that we are going to store our segment tree in the form of array. Okay, and the length is not actually 18, it is much more, but for now let's have this as our array. Okay, now let's consider the range from 0 to 5. Okay, and my segment tree will start from index 1. So this 1 is actually keeping track of the index that we are going to populate, okay, in our segment array. Now let's consider a value that we are going to search in this range 0 to 5. Okay, we want to know whether these two overlaps in this, and of course it does. Okay, there is a partial overlap here. It occurs in this range 0 to 5, but there is no total overlap. Total overlap will happen when we have range 2 comma 2. Okay, but for now it's like this. So what do we do in this case? How do we find out the number of ranges, like the left and the right, that will have 2 in it? Okay, so for that, I'll split my range into half. I'll have 0, 2 and 3, 5. Okay, it's half of this range. Now what is this? This is the left child. This is where the left child will be stored. Okay, and this is where the right child. So this is the left child. This is where the left subtree starts, and this is where the right subtree starts in our array. Okay, now let's move further. So we still don't have a total overlap. It is 2. We still don't have it here, right? So we'll divide it further into half. There you go. Okay, 0 and 0 to 2, the range is half, to 0 to 1 and 1 to 2. And similarly, these are the index of its left subtree and right subtree. Okay, it's still not overlapping with 2. Okay, this is not entirely, it is not even in the range. Okay, this is out of the range. 1 is less than 2. Okay, so it is not within the range, so we don't actually have to explore this at all, right? Now we'll check in this range. We still have a partial overlap here, right? So we'll explore it further. Now, how am I calculating these indexes? For a moment, let me brief on that. So since our each node can have 2 children, okay, we will have a left and a right, right? So the reason I am starting my index array or segment tree from 1 is because it will be easier for me to calculate the left and right child, right? So the left child will be 1 into 2. So it's here, right? And right child will be 1 into 2 plus 1. So it will be 3. All right. You can do it from 0 as well, but it's pretty easier to calculate it this way. Now here 2, the left child is 4. 2 into 2 is 4. 2 into 2 plus 1 is 5. And similarly 5 into 2 is 10. 5 into 2 plus 1 is 11. This is the left subtree index and the right subtree index. Now notice this won't overlap at all. So we don't have to explore at all. But this is what I call as total overlap. So 2 and 2 is the exact range that I was talking about. It overlaps with 2. Now what will happen here? So once I find this, I know that at index 11, I have one common element, okay? So what I'm going to do is I'm going to take my pen and write 1 here. So initially, let's say this entire array is initialized by 0, okay? I'm going to increment it by 1. Now, what I'll do is I'll go back, okay? And once I go back, I know this doesn't overlap. So this entire thing will give me 0 and this has given me 1 overlap. So the total common elements in this entire range 1, 2 is actually 1, right? So at this index also 5, I can write 1, right? Then I go back here, okay? And this doesn't overlap, so this also gives me 0. And this will actually the total range, the total number of common elements, okay? The range in this will be 0 to 2, and what will be my final answer? It will be 1. There is one range that overlaps. So yeah, we do have one common element, 2, that is right. So I will still have 1. So at this index 2, I have 1, right? Then I go back here and then I explore my right child. So right is actually out of index, right? So again, we have 0 here, and then I check whether do they overlap. Yes, we do have 1, right? So in 0 to 5, there is one common element that is this 2. So we have 1 here at index 1, I can have 1. Okay, this is how. So I'm going to do it for this number actually is I have just taken an arbitrary, but I'm going to do this updation. Okay, I'm going to populate this for every value inside my nums1 array. Okay, and then as I find my current value in nums2, okay, in that I am just going to explore. I am just going to find out all the range. So in that case we'll have a range like this, right? So in this case I will only have a value and I will check whether this is a common value or not, right? It's a common value, then well, we will populate this. But when I am iterating through nums2, okay, when I find the index of nums2, in that case what I'm going to do is I'm going to pass a range of values. Okay, so that range will be like, I don't know, maybe 0 to 2. Okay, it might be this range, and then within this range I am going to check how many values are overlapping, and in this case it's 1, right, at index 2, right, 1. So this is what I'm going to return. Okay. Finally, let's code it out. So here in my code, I have initialized my segment tree and the methods that I'm going to use to manipulate my segment tree. Okay, so I have initialized my segment tree as an array of length 4 into n plus 1 and with the values as 0. Okay, now let's check our first method that I've defined here. So I'll just go through briefly what it does. So as I mentioned, my segment tree will be an array, right? So to iterate through the array and to go through each of its children, I need an index, right? So that's what I'm using here, tree index. Okay, and similarly I have my start and end ranges in which I'm going to check my value, okay, whether it falls in this range. Now the thing is, I need to check whether this value is within this range. If it falls out of the range, then obviously there's no overlap, so I just return. Okay, now in case if it is total overlap, so if my range is something like 2 and there is 2 and here I have 2 again, so that means there is a total overlap between them, right? So in that case I am just going to simply increment the tree index, the child, okay, of that particular range. Now finally, when I have done these base cases, I will go through the actual ingredients that make up this entire tree method. Okay, so what happens here is I am going to divide my ranges, okay, this range into half, okay, and I'm going to recursively go through each of those, the left side as well as right side. And meanwhile I'm doing that, that is nothing but my index has been called on to the left child of my main tree index and the right child of my main tree index. Okay, so the thing is I am going to start my tree index from 1, okay, and let my, for example, I've just taken my start as 0 and end as 5 and my value suppose 2. Okay, and the reason I'm starting it from 1 is simply because it's easier to calculate the children using this formula. The left child of my tree index in this array will be 2 and the right child will be 2 into 1 plus 1, so that will be at index 3, right? So that's what is going to happen. You can, if you want, use 0 based index as well, and that is completely fine. We can use it like this and like this, but for now let's keep it simple and we have it this way. Now we'll pass this tree index and the halfened or divided by 2 range, okay, and similarly we are going to search this value within this range. Okay, once we have come out of the left and the right ranges, we have updated our values here. Okay, once we find the overlap, total overlaps, we have updated the values. What we do is, for the current value, what we'll do, we'll find all the values that are updated in our left subtree, and all the values that are updated in my right subtree. So that node will consist of all the overlapping values. So this value is present in the left ranges as well as right ranges. Okay, and we are simply going to add the value. So if it is present, suppose from 0 to 2, from 3 to 5 it isn't present, right? So it will 3 to 5 will return me 0, but 0 to 2 will return me 1, and as well as 0 to 1 will not return me anything, so that will return me 0, but 1 to 2 will return me 1 again, and similarly 1 to 1 will not return anything, but 2 to 2 will return me 1. So we have in 3 ranges we have 2, right? So 2 2, 1 2, and 0 2, right? And then finally from 0 to 5 we have. Okay, so total that will be our total here. So anyway, I hope you understood this part. Now let's check the other method. So in this method, it's almost similar to this. It's almost entirely similar to this with one exception. Here we are checking for overlap of 1. Okay, and we are updating our index here. See, if you can see, we are updating once we find the total overlap, right? But in this case, we are going to find the count of common numbers, okay, within this this given range and the range of our entire tree. Okay, so it's similar. We have this tree index as well, which is starting from 1. So the thing is, we will check whether our index overlap of these ranges, the given range as well as the tree range, whether they overlap. If they don't overlap at all, then we just return 0 because there is no common in numbers between them, right? Otherwise, what we do is we check whether there is a total overlap. Okay, so if there is a total overlap, then we definitely know that in this tree index we will have all the count of the common numbers in the range. Okay, this given range, right? Because if it was 0 to 2 and our range our given range was 0 to 2 and our range was 0 to 5, so we are going to go deeper, and then once we find 0 to 2 in that index, in that tree index, we will have the count. Okay, we'll have the count of the number of common elements that are present in both of these ranges. Okay, 0 to 2. Okay, anyway, so now we come to the partial overlap condition. So it is similar to this. We just divide our range, the main range of the tree, into half, and then we explore the left and the right subtrees. Okay, giving our mid as right and left appropriately. Okay, start or end appropriately. So if it is if we are searching the left end, then our mid has to be the end, and if we are searching on the right side, then our mid has to be the start, right? Mid plus 1 has to be start. So once we check here, we go recursively, we find all the counts. Okay, so once we find all the counts in the given ranges, we are simply going to add it up. Okay, and that's what we are going to return. Okay, so once we add it up, we have the total count that of the integers that are present. Okay, in both of these ranges. These are common elements. Okay, hope that is clear. Now let's jump into the actual algorithm. To this, let's start building an algorithm. So first thing we'll need is count. Okay, so which will be our final result that we return. Okay, count of the good triplets. Then what we need is our length of nums 1. Okay, so the n will be common, so I don't have to do this again and again. Okay, and nums 1 and nums 2 will be the length of them are same. Okay, so it will be common number n. Okay, and then finally I want to map my nums to numbers, the numbers present in my nums 2 with its index, right? Nums 2 index map. Okay, there you go. It will be a dictionary. Now I need to populate this nums to index map. So let me copy it and let me have iteration from I in a range of n. Okay, and I'm going to populate my nums 2 At index I with index I. Okay, I'm going to map the numbers. Okay, then finally what I am going to do is start with my actual algorithm. So here I need to iterate through my nums1 array, okay, which will be same range of n. Okay, and here I'm going to gather this, okay, this part, but instead of nums2 I'm going to have nums1. So what this will give me is, so on the left side if you can see this 2, okay, I'm iterating through this location. I want to find the index of this element in this array, right? So that's what I'm doing here, right? Mapping. So this entire thing will give me that, will give me the index of this particular element in nums2 array. Okay, so let me write it current, okay, or it can be like as big as current index in num2. Okay, we can do that, but let me just write it as current because I can make typos. Okay, so once that is done, what I want next is I want to keep track of my previous, okay, previous common, or what we can call it is common. Okay, so I'm going, as I mentioned in explanation, what I'm going to do is I'm going to iterate through all of these values, right? These common values, and I'm going to check whether it was present, like is there anything common, okay, between this index's previous values and this index's previous value, okay, between these two ranges, is there anything common between these? We can see it is not, okay, but the computer doesn't know that, so it has to find the common elements. Okay, so for that now this will be very helpful. Okay, so I'm going to copy this because that's what is going to return me the answer, and as I told you, I'm going to start my journey from 1. Okay, my index is going to be from 1 and this is going to be from 0, and like the total range that I'm going to give, and n minus 1. Okay, so n minus 1 because I want the range to be inclusive, right? And then finally the given range. Now what will be my given range? So I want to check this, right, this part, and what I'm going to update my segment tree with is my nums1. Okay, so I want this range and I want to check whether it overlaps with the other range, right? So what I do is I am going to pass 0, comma, current minus 1. Hope this makes sense. Now that we understand this part, we can now go on to find uncommon elements. Now how do we find that? Let's take the example here as 1. Okay, let's say our current index, okay, was this part, okay, 1 at that index, and here we are trying to find the common elements between this range and this range. Okay, so if we found the common element in these two ranges, the common element is 0 here, right? We already found that, but we also know that 2 is not the common element. Okay, how do we know that? So this in entire range and in this entire range exclusive of 1. Okay, so this entire range and this entire range, the common part is 0. So how many uncommon elements will be there? Well, it will be this whole I minus the number of common elements. Simple, right? So that's what I'm going to do here. Now once this is clear, we can finally find the the common elements which are occurring after this one. Okay, so how do I know after 1 what will be the common element? What I do is I find the total, okay, which is n, and then I subtract this entire current. Okay, that will give me the range of the right side, right? This range. Using this find count, what I can do is take this element, okay, the uncommon, okay, the uncommon elements, okay, and then subtract with this length. Now why do I do that? It because if this part, okay, this 2 was common, then I would have already considered it in my common part. But since it is uncommon, so definitely, okay, definitely it is not occurring in this part. So if it is not occurring in this part, that means it is definitely occurring in this part, right? So if it is occurring in this part, then we can subtract the uncommon part, right? Because it's, if it is already occurred here, then it will definitely won't occur here, right? So we can just subtract all the uncommon parts from the total right subarray, okay, like the count of the right length of the subarray, and then we will find the common part. It's that simple. So what I have here is uncommon will finally be our n minus current and minus 1, because I simply have to take account this value as well, and then I will subtract my uncommon here again. Okay, hope this makes sense. Finally, once these two are done, I know my common as well as uncommon part from my left and right subarray. So I simply have to increment my count to, what do I have to increment to? Uncommon multiplied by uncommon. Okay, so once that this is done, what I need to do is simply update my segment tree with the current value. So I am going to start from 1, and this is from 0 to n minus 1, and I am going to update the current value. Okay, I think, yeah, so this is my final output algorithm, and let me return the count and run it. Yeah, I did not have this n here. Yeah, there you go, finally accepted. And that's it. Thanks for watching.